Hi everyone, welcome to Unit Masters session. Today we have Hoon Kim. Sorry, hi Hoon, welcome. We'll just wait for like 2 minutes, have some more people join in.
Sure. Hello, everyone. Glad to be here.
We have Myra, Yip from Unit as well.
Hey everyone.
Yip, love the background.
How is it? Can you see it correctly or is it mirrored?
It's perfect. It's perfect. Can you send it to me? I'll update mine as well right now.
It's in the Telegram chat.
Okay.
Hey guys, right into the text, into the chat, where you're from, what you want to take out of the session. Kaiso, Philippines. Cool. I'll mute myself and hand over to Anchor. Or Anchor, you need a minute to update your screen.
I was just doing that. Okay, I'll just continue. Sorry, it won't take anyone's time.
No, take your time. No worries. Okay, we'll start like basically officially the session in a second to introduce yourself, and then like Anchor will introduce you, and then the stage is all yours. And I think you have the settings already to be able to share your screen. And after that, guys, it's very important that you all pay attention and write down your key takeaways because you will need to fill the key takeaways for this session in order to claim your certificate. And hopefully all of you have had the chance to claim the certificates for weeks 1 and 2. And if you haven't and it expires, don't worry at all. You will be able to claim the certificates in about 2.5, 3 weeks of time again. So no need to panic. Everybody who put in the work will receive their weekly certificates. Just so you know, because some of you texted us and everything is like kind of designed in a way that nobody will be kind of left behind if they did the work that they were supposed to do. All right.
Okay. Shall we go? Have we have 62 people. People will join in. Let's just start. So, welcome to Unit Masters. This week's session, we have Hoon Kim with us. Hoon is the CTO from Astar Network. Astar is a multi-chain smart contract platform, and where you can build smart contracts. Hoon started programming at the age of 12, and he won the gold prize in the Korean Olympiad in Informatics national competition at the age of 16 through his game project. His first contact with blockchain technology was in 2015 through Bitcoin. He became captivated by blockchain technology when he realized it could be used to innovate and at an unprecedented scale. In 2019, during his late undergraduate years in Japan, as a major in business administration, he worked on a thesis on using interoperable blockchains for corporate asset management and created his blockchain using Substrate. Unit is also built on Substrate. This project caught the eye of Watanabe, who invited Hoon to work at A-Star Network as one of the early members. In 2020, Hoon won the Outstanding Thesis Award for his university for his work. Now he is the CTO of A-Star Network and working hard to create Web3 that everyone can use. So welcome, Hoon, once again, and over to you. Today's session is all about consensus, mechanism, algorithms, and what and why are they required in the world of blockchain? So welcome, and over to you, Hoon.
Thank you so much for the introduction. That was really great. Yeah, today I'll be talking all about consensus algorithms and consensus mechanisms. Same thing. Although this topic is going to be mostly about the history of how consensus algorithms, or I guess P2P network consensus works, and then the application of blockchains. I did prepare a full introduction, but Anchor did a great job at introducing me, so probably I can just skip this one. And yeah, let's look into our agenda. So first, I'll start with the introduction of how network communication works. So we're going into like really deep fundamentals of communication in general, and we'll look into P2P networks. What are P2P networks? How does topology work? What are some challenges involved in P2P networks? And then that's where the meat of the story, consensus algorithms, comes to play. Well, with the Bitcoin white paper, and in the Chapter 5, I'll talk about some other consensus algorithms that we have right now, and how do they work, and why do we have so many consensus algorithms? And then I'll summarize the entire topic. So yeah, let's jump in. Now, before talking about consensus, like what is a network, right? Consensus, in its dictionary definition, it's essentially an agreement between a group of people or entities. And in a network, it means that when there is a new information or message coming in, people have to agree on how this information should be accepted or processed. And that's essentially what a consensus is in a network sense. But network itself is in a computer for computer networks, it's a little bit more interesting. So this image is probably you might have seen this if it's quite everywhere. It's basically shows the how internet is connected between places to places. What we call the internet or the World Wide Web is actually a physical cable that's undersea, physically connects ISPs, internet service providers, or servers. And when we're talking about networks and communications between computers, they're essentially sending messages from one computer to another. And how do we transfer messages? Well, through these cables. And with Starlink now, there's also one we also have a wireless signal up in the stars. So more ways to stay connected with people. And when we're talking about network interactions, this is pretty much how it is if you really boil things down. A computer can either send or receive, and of course I'm oversimplifying here, but they can essentially send or receive a message. And the cloud here is a common standard of communication. So both message format and message medium, how are messages transferred? And I just represent that as a cloud because it's like way too complicated. We just want to simplify it. And computers are essentially or the internet is essentially like this. We're just communicating with each other. Either we have a central server or we have a decentralized server, different topologies, how messages are being sent to each other, and how do they solve problems and how do they achieve their goals. Of course, I'll talk in detail about this in the coming sections. So yeah, a communication can be summarized as this: like, what message do you want to send? To whom should you send this message? And what message should you accept or ignore? And keep this in mind as next section, we're going to talk about P2P networks. So to contrast a little bit, we have two major models of networking. One is the client-server model. Another one is the P2P model. A client-server model essentially has a central authority or central server where multiple clients will connect to. And here, the aforementioned components, it can be expressed as, to whom do you send? Well, the central authority server. So it could be an URL, an IP address that's directly referencing that network, or it could be an identity or whatever. In a distributed server, and by distributed as in like not P2P, but like how AWS is distributed throughout the world, and you have a mirror server of each other. You can use a load balancer to distribute the traffic that's coming in. But in the end, you'll always connect to a single computer, a single server, where a centralized organization has total authority over it. And the clients, whatever message, what message should they accept or ignore? Well, it's whatever the server says. If the server says ignore this, then you have to ignore it. If the server says accept this, then you accept that. And what information you send is also determined by the server. And that's why in traditional networking, we also use the term master client and slave client to reference the relationship, as in you have the central master and the slave, which just does whatever the master client says the slave client should do. And the reason why both of them are called clients here is because even in a client and server model, we think of, when we say server, we think about this like big data centers and it's like massive data farms, which I mean that is kind of true how it works, but in terms of technology, it's fundamentally just another beefed up computer. It's just a matter of where do you point to, what's the address in order to communicate with this computer to achieve certain data. In a P2P model, it's a little bit more nuanced because there is no central location. You have to, and in fact, even the information itself is quite distributed. So there's no way to have a single authority. And in fact, the whole point is that we don't want to have a single authority. We want to distribute that throughout the network and connect to each other. So the who do you connect to is a little bit challenging. And depending on the protocol, they have different ways to achieve the who part. What information should you send is also different from a client server model, and which information to ignore or accept is also challenging because thing about P2P model is that you cannot make any assumptions. There is, without an involvement of a trusted third party, there's no way to determine if a certain information is indeed trustworthy or if it's correct or if it's malicious. So some of the client characteristics.
Hoon, could you slow down a tad bit, because most of our participants are relatively new to the space, so just a tad bit.
Sure, no problem.
Thank you.
Yep. So the in terms of characteristics between a client server model, first, client and server model works by giving total authority to server, as I referenced before, the master and slave relationship. Now, one of the best, I guess, upsides of this is that it's really fast. Since it's really simple and fast. You only have one location to reference to. You already know the information, whatever the server tells you. It's easy to configure because of its simplicity. The topology is easy. You just have to have a single reference point for all networks to connect to. And it is quite scalable in a sense, because if you need more memory, just add more memory, just beef up that computer, add more computer to it, pay more basically, and the network will scale just based on the resource of that single entity or single network. But there are some problems with this model. Now, namely, it's that it has a single point of failure. So if one computer goes down, one server goes down, then all connections to that server will be lost. Even if you have a backup server, a mirror server, or you're using a load balancer to reroute different traffics, it is still tied to a single entity. And by entity, I mean a legal entity or a physical entity, which can act as a point of failure. And this also means that it's also weak against censorship. And because of this, there are a lot of controversy behind this. And even in gaming, I think one good example would be recently when Ubisoft in their great minds decided to take down the one of their, I believe their Uplay server, and during that process, certain DLCs were made inaccessible to players who already bought the game, and they cannot re-download certain games on Steam, even though they bought it. And this happens because it's kept in a behind a single service and a centralized server with a centralized entity. So it's whatever they wish to do. You buy something in the internet, and if it's a digital content, most likely you don't own that if it's stored in your server. So I like to call it, like, if it's not your server, it's not your data, basically. Now, P2P has the exact opposite characteristics in that sense. So now P2P is when multiple clients or nodes, networks come together to share their resource in a decentralized, distributed manner. So no single authority. This means that it's censorship resistant. No matter what happens, if one node goes down, the other node should be able to take over. There is no single entity to really take down or do anything to. And it's trustless, as in like you don't really have to. Well, a good resilient P2P, at least. It's hard to say like it's completely trustless because there are P2P protocols that are very insecure, which I will talk about. But an ideal P2P should be trustless. You just go in there and you should be able to use it. It's also very resilient because of this. It's quite fault tolerant, as they say it. And now, there are some problems, which the insecurity, as in P2P network is essentially you're offering your physical computer, your physical device, either it's space, network, bandwidth, whatever, to a mass public of people who you have no idea who's connecting to. So anyone can essentially hack your computer if it's not secure, if the methodology was not secure, or you could receive information that you did not expect at all, and you don't know which node is trustworthy, or how do you trust certain information that comes in. And it's also difficult to scale because the number of cycles for connecting, for establishing connection or for indexing, also grows with the number of nodes that are in the network. Now, right now, the most common commercial services are hosted in a client-server model because they have to offer the best user experience possible, and they are charged in exchange for that service, so they can sustain themselves and maintain the servers and scale the servers. Imagine if a Google was P2P, it would be very slow, insecure, and unreliable. So no one would really use that. But then again, if it's a P2P system, then people wouldn't really pay money to use that in the first place. But having said that, because of current situations in both, you can say politically, how it's socially impacting, or even how, in a technical sense, like how unreliable certain servers could be, how dangerous a centralized network could be. There are a lot of researches on P2P. So what are some other challenges that we have with P2P? Now, the biggest issue with P2P connections is definitely when it comes to trust management. As I said before, you have to you're basically offering up your computer to the mass. Like, how would you trust this? And in a more algorithmic way, which information should you disregard or accept and write on your hard disk? There's a whole research field about this, and it's a huge problem, which blockchain technology does solve, and that's the whole point of the consensus algorithm, which I will go into detail later. Another problem is with the resilience of a system. So the famous example would be the Byzantine generals problem. Essentially, what this thought experiment does is it shows how interconnected distributed systems can make a decision work together, even if one node has a problem. So in the paper published by Lamport and et al. At the 1980s, I believe, the author just uses Byzantine as like an example, but I believe originally it was called like the Chinese generals problem or something like that. Yeah, it doesn't have to be Byzantine. It's just like for some reason he chose that as an example, probably a huge history fan. And the idea here is that, let's say we have a general, a collection of generals who has to make a decision to either attack or retreat as part of their strategy. But this can only be successfully executed if other generals agree on this. But what if there is a traitor amongst the generals? And the communication is completely done orally. And when I say oral communication, it means direct communication. So because there is no trusted third party or a overall governing body in this case, the general is only aware of communication that went through directly his ears, and he's only aware of the orders that he gave. So, and as an example, the trusted general number one, for example, told general number two to attack and general number three to attack. So, and he was told to retreat from two generals, but general number one has no idea what general number two said to number three. And that's the nature of P2P, is that outside of your direct peers, everything else is a black box. So there's no way to understand who is right or wrong when there are conflicting information coming in. And that's where, yeah, this experience comes in. Like, you see that the general number three, the one that looks like he just got a divorce warrant from Karen, he is a traitor general, who is essentially like a faulty general. So a general with who's giving out wrong information or incorrect information. And he tells one general to retreat while the other general to attack. And you can see in the top right box, it says what the general's perspective, this is how the network situation is. Three generals, one is going to attack, but two wants to retreat. And number two says two generals wants to attack, but one general wants to retreat. Now, the solution is, there are solutions for this, which is follow the majority order. And as long as there is a majority of the generals are a loyal, trusted general, then the network can disregard the faulty ones, which is also how blockchain sort of solves its issue regarding the 51% attack, which I will discuss later as well. Another issue with P2P is that lack of identity. So because everything is technically anonymous, it's very easy for a malicious player to hack or attack a certain system and get away with it. So it's like the Wild West. How can you regulate things when there is no trusted third party or a centralized organization or authority? Another problem is with cyclic dependency, as in if the network node is oblivious to networks that they don't have direct communication to, then what happens if there is a cyclic reference, as in, let's say node 1 is referencing node 2 and node 2 is referencing node 3, but node 3 is referencing node 1. So node 1 doesn't receive I guess a full answer because it's just going in circles at that point. And this goes into, this presents a deadlock. Another problem is with the distributed trust data, as in when you're saving your information in a P2P network, if you want to store something, unless you don't want to store that in a single computer, because that defeats the purpose of a P2P. So you want to store that to all the other computers in the network, and then retrieve them whenever you want to download that. But that also means that you have to entrust that other personal computers have your personal data, and this becomes a problem. What data can you trust to store, or what should be stored? Now, there are key researches that actually tries to solve this issue, or at least address it, and it's quite fascinating while I was researching this. So yeah, there are three major research that I guess was really notable for me was the GNU-Tella project, Cohort. There's also three other projects alongside Cohort that in the same era that describes the technology that it describes, and the PACE project. So GNU-Tella is probably the first ever P2P protocol of its kind. It is not really a software. It's more of a protocol of how to establish P2P connections and file sharing. In fact, one of the most well-known GNU-Tella client was LimeWare, which is sort of the predecessor of Torrent. And so you know how influential this was. And funnily enough, GNU-Tella, the name is like a portmanteau of GNU and Nutella, because programmers are really good at creating names. And Nutella, that's why kernel devs are so fat, I guess. But anyway, I have no hate for the kernel devs. I love them. Can't live without them. So yeah, jokes aside, it's quite the algorithm for Nutella is quite primitive, but it was able to achieve its purpose at the time. So the way how it works is when a computer runs a Nutella client, it has to bootstrap itself by and connect to at least one node. And this could be done by either using a already known address, or you could reroute addresses and find. There's a bunch of ways to do this, but it will basically try to find other networks, and networks will. Because every network has at least reference to one network, when you connect to another GNU client, it will be able to reference each other. So if you want to perform a search that's only possible, that's only stored in a certain computer, it will go query in every node. Nodes will pass that query to another node that it's connected to until it gets a hit within a certain amount of hops. And then that's how files are transferred. Now, the problem is it's quite slow. It's not secure at all, and it's not scalable because the number of hops or number of cycles is also depends on the amount of connections you have. So more peers in the network means a slower search result because you have to go through so many clients. And it's also unreliable because if a computer shuts down, then the file transfer is just finished from there. It doesn't really, in order to start again, you have to query another client. And considering that these are all personal computers, it's really hard. It wouldn't really be a reliable system. A Cohort is a distributed hash table. So basically it has, and I won't go too detailed in this because it's really complex, but basically it's kind of, before we had distributed ledger technology, we had like distributed hash table. That's how I would sort of describe it. But yeah, Cohort or distributed hash table plus GNU is kind of like how torrent works. Basically, each node has a reference to a hash of a system within its network. And this is called a finger table, because it's a finger is when you're pointing to a node that goes clockwise or clockwise to your circle. And it's quite interesting because now every node must contain a reference of a finger table, and it must update that periodically. So even if a computer goes down, you still have a reference. You'll always have a reference to the latest node, and you can easily boot that up and then just do another search and see which one hits. But basically, kind of like how blockchains work in a sense that it has a distributed information. It uses a hash table as well. PACE. So this is the first ever decentralized application architecture. It's not really a technology or protocol, but more like a formalization of how a distributed application should work. And I believe this is the first time when it was formalized in a P2P network. You still have, you have the communication layer, information layer, the trust layer, and the application layer. And decentralized application in this context refers to something like torrent or any other like P2P apps, not dApps, as we call it in the blockchain space. And the trust layer is what's interesting, because this is exactly what blockchain sort of solves with the consensus algorithm. So yeah, regarding this, from this research, we were able to establish decentralized communication, decentralized discovery through Cohort, decentralized fault tolerance with Cohort's finger table, and a decentralized app architecture through PACE. But how can we manage to this decentralized trust, the trust layer that PACE refers to? Which information, when there's so many information coming in from various nodes to your node, which one should you accept? There is no formalization for this. And that's why even with the torrent or P2P file sharing applications, they have a static file and a hash of the file just to verify that yes, it is the correct file, it's the correct byte size, so therefore you can accept that. But it's very static. You can't dynamically change the content of what's being shared. You can only share the same exact file. And before we can talk about like how this trust management, decentralized trust management works, there are two notable works in the past. So one is Hashcash by Adam Back, made in 1997, and the reusable proof of work made by Hal Finney in 2004. And now we finally went into the keyword here, proof of work. So proof of work is it's not invented by Bitcoin, surprisingly. It was first introduced through Hashcash, which is a tool for filtering email spams or DDoS attacks. the idea here is that users are solving a cryptographic puzzle that's easy to verify, but hard to actually like solve with a dynamic adjustable difficulty. And the idea is to make sure that spamming is not computationally lucrative. So it's not worth spamming if it takes so long to actually get send something, or to actually get create a valid proof of acceptance. And reusable proof of work extends this the traditional proof of work by Hashcash by adding the concept of sequential reusability, which did my internet just get stopped there for a moment? Sorry there. So yeah, reusable proof of work. Basically, when you generate a token, and by token I mean like a hash string, or a solution from the proof of work, it could be exchanged to another user if you go through the reusable proof of work, and this solution will be provable and will retain the same value and allow you to exchange from one user to another, making a chain of transactions essentially based on this token. Now, both Hashcash and reusable proof of work stores a local ledger in the client for the list of exchanged proof of work tokens, as in they have a ledger of transaction histories to see like who you transferred to, and that way you can verify if they have already been transferred or not. And based on this work, Nick Szabo, I believe that's how it's pronounced, proposed a hypothetical program project in his blog in 2005. Probably he's Satoshi Nakamoto. I don't know. Well, my vote is actually on Halfini though. But he proposed a P2P system that doesn't rely on a central authority. How you can still validate state transitions in a decentralized way by going through a benchmark function, as he puts it. And the last created string of BitGold, the project is called BitGold, and the last created string of this problem that was first introduced using the proof of work concept in Hashcash will be the challenge for the next transaction. And essentially, he established the concept of proof of work consensus and the transactions through his project. And there was another separate blog post. It was more of a text file, but yeah, by Wei Dai, who proposed a P2P system similar in terms of solving computational problems. But interestingly enough, you would only mint tokens through solving problems, but maintaining transactions can be done by any node that has a collateral of a certain amount of tokens in their server. So he kind of described what we call a proof of stake there before Bitcoin was a thing. And the way how he keeps a ledger of interactions of credited and debited transactions in this decentralized system sort of resembles a UTXO. And also he used the word smart contract a lot. So yeah, now the problem here is we know how to find peers and all that good stuff in a decentralized network, but back to the question, like how do you create trust management? How do you establish trust management? And according to these two, the answer is, what if a node can solve a computational puzzle, and whoever can solve this the fastest will be the accepted transaction. And for a valid transaction to be valid, it has to be the latest as well within the network. And that's where the Bitcoin white paper comes in, which sort of formalizes all these concepts. So I guess the key findings that Bitcoin made was formalizing the concept of a distributed ledger. So all nodes will contain a ledger that's distributed throughout the network, a P2P network. So everyone has a reference to every other thing, information and state transitions that other networks has been performing, and a chained block-based state. So every state represented as a block, and that block will contain a hash of a previous block, meaning that because the hash it is a deterministic and you can easily prove it just by comparing the hash of the block's hash and the actual hash in the block. And if there's a discrepancy, that means there is a forged block. So in order to fix the entire network and be accepted, you have to change every other preceding blocks up to the point of the fraudulent block. And finally, the consensus algorithm, what transaction should be accepted, what message should be accepted and stored as part of a block. Now, I've already explained this, so I'll skip. Proof of work and mining. So how it works is basically a node, or the network itself actually, will send a puzzle in the form of a nonce or a hashed nonce, and the users must brute force that hash with every other nonce that they could guess, and then if they can guess the correct nonce, then they'll send the proof to the network, and then that would be accepted, and that will be a part that solved puzzle will be basically treated as a block, and it will be stored in the ledger. So what are some consensus algorithms that we have here? Now, first, a consensus algorithm can be essentially seen as a algorithmic trust manager. It defines which node can claim that their new information is valid. And there are several problems here with the traditional consensus algorithm. And by traditional, I mean proof of work. But yeah, after one side note is after the release of Bitcoin paper, like so many new innovations has been happening. This is a amazing graph provided by the Blockchain Consensus Encyclopedia, listing down all the known consensus algorithms and issues common attack vectors for a blockchain. And yeah, I'm not going to be talking about all of them, but it's really interesting to see how people can come up with these crazy ideas and how fast the space is evolving. But yeah, so the limitations of proof of work. Well, first, it's very slow because remember, like you have to brute force a hash, and that is the difficulty is adjustable. But as the network participants grow, the difficulty will grow. And as the price of Bitcoin goes up, of course, there's going to be a lot of miners. So it is just wasting a lot of computational power. And yeah, it's really a high resource computation. Also, it has non-deterministic finality. What does this mean? Basically, when do you know if a block is part of a blockchain? You know that if a node solves this the cryptographic puzzle and it submits that will be accepted throughout the network, yes. But it still takes time to propagate. And during that time, there's going to be other miners who's trying to verify the current block header in their own way, right? So there's like parallel computing going on here. So who is going to be the first? And in Bitcoin, it's basically whoever has the longest block and the fastest solution can claim the latest block. But you cannot prove that the node that you're connected to will have the final block. You can only know that after a block has passed. So it takes a long time, but also you cannot be guaranteed that your transaction will be passed, which makes light clients even nightmare to integrate. It has a horrible scalability as well because both computationally but also storage wise. But that's not really specifically to POW, but more like Bitcoin, the way how it's structured. Now, having said that, there are up points, like several advantages of proof of work that's still very valid to this day, and that is that it's extremely permissionless, meaning that there is no on-chain requirements to be a validator. You just need the right hardware. And you can argue like, yeah, but I mean, I need a lot of expensive gear to set up this mining rig, right? But yes, I mean, now that's the case. But if it's dynamically adjusted, so if there isn't beefed up rigs in the wild, then even a cheaper computer can mine Bitcoin. But then again, at that point, there's going to be more competition, right? So it's like a self-adjusting, interesting mechanism there. And it's also unstoppable because there is no central identity or authority involved in it at all. Everything is decentralized. Everything is free for all. And in terms of, I guess, token economics, it also has a rather clear economic value. So when it comes to proof of stake or any other alternative consensus algorithms that requires a down payment, it depends on the price of a token. But in Bitcoin, there is no it doesn't care about what the price of Bitcoin is. It could start from zero, it could start from $1 million, whatever. But in the end, for the people who are producing that token and who are expecting to sell, they're expecting to sell for a break even, at least a break even. So the floor price generally is the cost of mining or maintaining, and like before every other blockchains were a thing. So what are some other alternative consensus algorithms that are currently in use? We have the proof of authority. So the proof of authority is basically, as it says, authority-based validation. So only a whitelisted set of nodes are able to validate transactions. It is very centralized, so it's like going into the other way around. But it still is, in a technical sense, peer-to-peer, because it does have a peer-to-peer architecture or topology. It's just that the authority is embedded directly within the blockchain itself. So it's much faster for sure, scalable, but extremely centralized, which will turn off a lot of people. And it's it's easy to implement though. The problem here, well, not really a problem, but I guess the use cases, would be that it's perfect for private blockchains or consortium blockchains, and it still maintains that blockchain architecture, so you can still create bridges and it can still be treated as a blockchain. Now we have the proof of stake, which is this proof of stake is the variant that's going to be used on the Ethereum blockchain after the merge. And in this proof of stake, validators must stake a certain amount of tokens to a smart contract or whatever account, and they are able to validate. And they're able to validate and also receive rewards. Now, staking amount will act as a collateral. So if you're misbehaving, if you're sending malicious transactions, and the network detects that, then your collateral will be slashed. So your idea here is that, the assumption here is that you will behave by making sure that if something goes wrong, you will lose money for this. So it's more expensive to perform a 51% attack, which is where majority of the validating node in a network is a malicious actor. And yes, so the reason why proof of stake is considered to be more scalable and fast is because Bitcoin, as I mentioned before, every node is competing for a block. Every single mining node is. So this makes it really difficult to understand which one is the final block, but also the computational time grows proportional to the number of hashing power that's in the network amongst the miners. But in a proof of stake, your eligibility for being a validator depends on the amount. So if you're amount of tokens, if you already have that, you already have the down payment done, then you can validate. No requirement for hardware power. Of course, you still need stability and fast. You should be the fastest fast node or the earliest node to validate something to receive rewards. But you still can receive rewards regardless of your hardware in a theoretical sense. So it's low cost in terms of hardware, not the actual price of staking, and it's more scalable because there is less node and it's deterministic. So because you already know if someone validates a block, it just propagates that throughout the other validator nodes, which is a smaller limited set. Now we also have another variant of proof of stake, which is the delegated proof of stake. In this case, the proof of stake participants are not just the validator nodes, but also we have a concept of delegates, which is voted by the community. And the delegates will be able to perform block validation. And in this case, the rewards that was received through this when validating a block will be split amongst the stakers, which are the normal people, based on the amount that they have staked. It's kind of like being in a staking pool in a sense. And in this case, if a validator misbehaves, only the validator's collateral will be slashed. So the voters or stakers, they will stay safe. And the purpose here is to add a more democratic way of voting, because with the traditional proof of stake or the Ethereum proof of stake, it's basically whoever has most money will get more money. And well, that's totally fine. That's how capitalism works, kind of, sadly. But if you want to have more community participations and community stake on which node should be able to validate blocks and has more trust amongst the network, then that's why we want to add a more democratic aspect to it, which also goes into the next variant of proof of stake, which is the nominated proof of stake. So in this case, nominated proof of stake is similar with delegated proof of stake in a sense that non-validators can also participate in the validation process by staking their tokens to a node. But instead of having delegates who performs that, you nominate proof of stake, the token holders can directly stake on a validator node within a limited space. And then the network will randomly choose a validator set for that era. Era means era is a specific time span within a blockchain. That's I believe that's in Polkadot it's about like a day or something, and they have and they will be valid. There'll be a node will be part of the validation set based on the nomination that they receive, and nominators will receive a portion. The validators can receive a commission from the nominators for their work. However, in nominated proof of stake, the nominators, i.e. the people who are staking on a validator node, their reward can also be slashed if the validator misbehaves. So this adds another layer of consideration when you're choosing a validator. So you have to choose which validator is reliable, which one will provide reliable infrastructure, but also ones that will not produce a malicious transaction. And this sort of makes sure that the validators are always a good behaving validator set. So finally we go to the summary and conclusion part. In summary, you see, P2P is very challenging, and it's not reliable before Bitcoin. Now there are many researches, and all the way back into early 2000s, or the year 2000 actually, but it was still, the trust layer was formally defined. However, it was still not formally fixed or addressed without using a trusted third party. But there are several projects that were proposed by the likes of Nick and Wei, who proposed a POW system. Later, this was formalized by Bitcoin, and then it was which establishes the concept of a decentralized ledger, a consensus algorithm, and a blockchain structure. Now, after Bitcoin, we've seen so many consensus algorithms pop up, and that is fit for so many different use cases, which I believe makes big blockchains so a technology that's applicable in so many different areas, depending on how you structure that consensus algorithm or how you structure the network topology. And I just want to take a moment to appreciate how fast the space was evolving, because everything that took to make Bitcoin was kind of established within not even within 10 years. Like Astar from 2001 we had Cohort, 2003 Pace, 2004 reusable proof of work, 2005 and 6 we have Bitgold B-Money. Not really a study, but an idea that was closely resembling a Bitcoin. And then we had the Bitcoin. And after that, it's like a Cambrian explosion. So many things popping up, and it's really amazing to see how consensus algorithms are evolving. So in conclusion, the consensus algorithm removes the trust layer in a distributed system by setting up these set of operations and rules of what information should be accepted and disregarded. And this provides a proof of ownership, essentially, and state transition in a global P2P network that is completely decentralized and distributed. These are my sources, and thank you so much for listening to my long presentation. Sorry, I tried to make it short, but yeah, and let's connect if you're interested. Thank you.
Wow, Hoon, thank you so much. That was so insightful, and there's so much information for everyone to take in. So, but don't worry, the session's recorded. You can watch it over again and use the chat, use the study group. So interact. We have about 10 minutes. So we have a bunch of questions. So I don't think we'll be able to answer all of them. So, but quickly, I'll just run over a few and try to answer as many as possible. As briefly as we can. Uh,
Mhm.
Let me just scroll back up a little bit. Okay, okay. Just a moment. Yeah. Okay. So one is how many pairs are required for verifying a POW or a POS? So
How many nodes? Well, I mean, technically, you need at least two, one to send and one to acknowledge that.
great. Gonna
But
just come to
yeah.
this slightly
Uh,
longish. Yeah. Sorry. Please go ahead.
Oh yeah. Just to slightly add on to that, if you have two nodes, if one node gets compromised, that's like 50% of the network, and so it could go against the 51% rule. So that's something you should consider. But it's technically possible. Just you wouldn't really do that.
Right. Right. Got it. Question from Sayed. What do you think about how blockchain is going to fuse with the world of gaming? If you had a gaming project on Unreal Engine 5, how would you use blockchain and cryptocurrencies for microtransactions trading in your game? Will we have a next generation World of Warcraft in the new Web 3.0 world? Try to answer it as non-specific as possible, I guess, for everyone's interest.
Okay. Well, I guess to generalize the question, I guess I could say like, what's the application for blockchain technology in video games, right? And in that case, well, to be honest, I think that's a very long topic. Probably I could go hours in answering that. Simply put, there are a lot of potential in this space for sure. It's just that balancing the interest of corporates, developers, and players are very challenging in the video game space, because video game is an interesting type of service where it's sort of an art form that is controlled. So you don't want to have so many like, I guess, non-controllable factors, which blockchain does introduce for developers. For corporates, they don't see any interest in having a third or enabling a secondary market, like NFT market spaces, for example, where you can trade game characters or game skins. That's one good example that everyone uses. So there's no clear business model behind that, unless they're relying on the price of NFTs to go into the moon, which I don't think it's a good idea. For players, they get a lot of ownership, but right now the learning curve of the system is complicated, and there is no game project that justifies the, I guess, the usage of this technology. But I do see a potential, and this is just a matter of time until we see something that's more applicable.
Amazing, amazing. Sad. Hope that answers your question to a great extent. Next one is someone. If you could, Hoon, if you could just throw some light on proof of history based blockchain like Solana, and what's the scope? Yeah.
Okay, proof of history. So, well, sadly, I don't think I know enough about proof of history to really say, like, have a strong so yeah, to give out a lot of information on it. All I know is that it's, compared to the other consensus algorithm, it's a little bit more not blockchain-like. Hence why Solana was able to achieve near server-like speed and performance.
Right, right. Still very early days for the technology, right? Overall. There's a good question from Alan. There is a rise in the DeFi world, a concept called pledge mining, where you have to stake your token to participate as a validator. How do we how do we uh, how do we know the legitimacy and how secure the platform we joined is?
That's always a hard question, actually. I don't think there is a clear-cut solution or a clear-cut answer for this, because as everyone says, and probably this might be the only best answer, do your own research. You have to be knowledgeable. Don't expect others to spoon feed you what's the answer is. And I think that's the whole point of Web3 as a whole, is that you're an independent, sovereign individual. So you should be able to understand where you want to stake your money in or just be part of.
Right, right. So I guess that's, yeah. Gip, you want to
No, no,
just
no, no.
chime
Let's
in?
talk also. Final question. Yeah, that's about like Ethereum's move to proof of stake, and also the outlook for the other chains. I mean, Astar is on Polkadot. What kind of consensus mechanism is used there, and why did you guys basically choose to work in that environment?
That's a great question. Yeah, so I guess first, to answer your first question regarding proof of stake, the merge and the outlook, I think, like, to be honest, I don't have a lot of problem with that, because if someone says proof of work is better, and a lot of people say it's because of decentralization, we're like censorship resistant or something like that. In all honesty, if they have a mining rate, probably the only reason is because they want a profit out of it. If they want to have a fork of a proof of work blockchain or Ethereum, but they're not using Ethereum Classic, that means they're just going to dump that token because they have a free money duplication glitch right there, right? So that's sort of my opinion on the merge and people who's talking about having a fork of proof of work Ethereum, or I like to call it the Ethereum Classic 2 Electric Boogaloo. And outlook wise, it will not solve all the issues, but it will definitely be the first step and the right step in introducing new solutions for Ethereum. And regarding your second question, so what consensus algorithm for our network, Astar network, as a parachain? So first, Astar network is a parachain, and for people who don't know what a parachain is, it's like a shard of Polkadot network. Polkadot network is the layer 0 network that has its own validators. And as a shard, we actually share the same validator, which is, or the consensus algorithm is nominated proof of stake. And we share the same validators as Polkadot. So we do not require our own validators. We just need a collator, which is a full archive node that contains the information of our entire blockchain. So yeah, like that's I guess that would be my answer to your question.
Thank you so much. Ankur, over to you.
So I guess that's all of the questions for the session. Thank you so much, Hoon, for for that lovely session, so insightful, and I'm sure everyone's really learned a lot. And thank you for for your time and all the information that you've shared.
Thank you for having me. It was a pleasure talking here.
And nobody need to freak out. You already heard from the speaker also that even speakers like who work in this space and have been in the space forever don't need to know every detail about every kind of consensus mechanism out there, right? So no expectation that you guys know all about that, but it's good to know kind of the history of our industry, how it evolved, and where we stand today. And if you follow this, you will know that even within the space of the experts, people don't have a clear answer towards what is the best consensus mechanism and why and so on. So what I want to say with that, don't feel overwhelmed, but just take one or two key takeaways from today's session and then speak with them, like speak about these learnings with your peers and your network so that you develop this blockchain literacy or fluency, as we call it in Unit Masters. See you tomorrow for a workshop, hands-on workshop on how to create your own DAO, which is like the human protocol level of the human layer of blockchain and decentralized consensus. Thanks a lot, everyone. Bye-bye.
Bye.
And we're also having an AMA session about Unit Network, Unit Masters, and the whole thesis in about a minute on Twitter Spaces. So please feel free to join in as well. Thank you.